In this video, we're going to continue with our introduction to equilibrium, but we're going to focus more on graphical representations of equilibrium. So there's two types of graphs you can see when you're studying equilibrium. One of them is an amount, and that amount really should say concentration. So to represent concentration, we simply show these square brackets, okay? Oftentimes in moles per liter, versus time. So progression of reaction this way. And then the second type of graph is a rate versus time. So let's start with the concentration versus time. So basically what you'll notice is in a reversible reaction, you'll see your reactants are used up and your products are starting to be produced. At the beginning, you have zero product, but a lot of reactant. That's all you have in your flask. And over time, you'll see that the reactant starts to drop. At the same time, the product starts to go up. And what you'll see is there'll be a point where those processes flatline. And it's at that point that you've reached equilibrium because the concentrations have stopped changing. Once again, it doesn't mean that your reaction has really stopped. It just means the rate of the reverse and forward, they're now equal to each other, so it looks like nothing's happening. So for that reason, we say that equilibria are dynamic. It means that on the outside, the macroscopic properties, they stop changing, like color changes stop, concentration changes stop, other measurable features stop, but the particles are still colliding and reacting just at equal rates, so it looks like nothing is happening. So that's one graph you can look at. The other graph you can look at is the rate versus time graph. And so this is if we're looking at the reaction, A plus B produces C, and it's a two-way reaction. This forward rate is what you see here. So it's the one going this way. And the reverse rate would be C going to make A plus B again. And so in this type of graph, you know you've reached equilibrium when the rate of the forward and reverse are now equal to each other. Okay? And so this is where you've reached equilibrium. I want to be very clear here. Students often think that equilibrium means that your products and your reactants have to be the same as each other at equilibrium. That's not the case. It just means that the concentrations overall have stopped changing. But the products and the reactants do not have to have the same concentration. Equilibrium does not mean products equals reactants. It means the rate of the forward reaction and the reverse reaction are the same, which is what you see in this type of graph here. Okay, so that's a graphical representation of equilibrium. You can see it in two graphs. Understand the difference between these two graphs and what they're trying to illustrate. So what we're going to do is we're going to jump to how do we represent this equilibrium? We always like to take things and make them more mathematical. So there's this thing called the law of equilibrium, which basically means that if your system is at equilibrium, you can take a ratio between the products and the reactants, and you're going to get a constant. And that constant is called your equilibrium constant. The idea is that if you have a system and you know the concentration of products and the concentration of reactants, you can take this ratio, you'll get this equilibrium constant value here, and you can basically use it to see if you're at equilibrium or not. Because sometimes you might not be there, you're still trying to approach equilibrium. Remember, reactions don't necessarily start off at equilibrium, right? You'll notice the forward rate's really high here, and the reverse rate's really low there. And that's because at first, all you have is reactant to react, and you have no product. So overall, the forward rate starts off really high, the reverse rate starts off really low, but then over time, the reverse rate starts to go up because you start to make more product. The forward rate starts to go down because you start to use up reactant, and eventually there'll be a point where you think, wow, like this is going to surpass that one there. And really, no, they just kind of meet up. So the system kind of works towards equilibrium, provided you're in a closed system. So we can use this equilibrium constant to see, what is this constant going to be when we are at equilibrium, and are we at equilibrium or not? So equilibrium constant is represented by the letter K. It's an uppercase K, not a lowercase k, like in the rate constant, and we'll see the difference there soon. And how do you measure or how do you calculate the equilibrium constant for a system? Well, let's say we have this reaction over here. A, B, C, and D, the uppercase ones, they're all our reactants and products, and then little a, little b, little c, little d, those are our coefficients. So you're always going to do the reactants raised to their coefficient, the products raised to their coefficient, divided by the reactants raised to their coefficient. So for example, for this one here, the KEQ, you don't always have to put AQ, but that means K at equilibrium is equal to concentration of C to the power of C, which is the coefficient there, times concentration of D to the power of D over there, which is the coefficient, over concentration of A to the power of little a, because that's a reactant and a coefficient, times concentration of B to the power of little b over here. And this would be your equilibrium constant expression. So the idea is that if you knew the concentrations at equilibrium, you could plug them all into here, 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 and here, and that gives you your equilibrium constant. So the constant is the K value itself, which is a number, and then the expression is when you write the expression based on the equation you have for that reaction. Okay? Now, the nice thing about the K, the equilibrium constant, is that usually there's no units for it. There are technically units, but they vary so much, we just don't report it with units. So we don't have to really worry about our units too much in that scenario. And the other thing, though, about the K is that it does vary with temperature. It does vary with temperature. So typically when you are reporting a K value, you do have to state what temperature you're recording that K value to or for. And lastly, this is going to be an interesting one. When we are trying to write these equilibrium expressions, solids and liquids, they're not going to be included in the expression. And the reason for that is because solids and liquids are usually pure substances. And so their concentrations don't really exist. They don't really change. They're constant. It's like if I had a glass of water, and then I pour some of the water out. Just because I lost water from the initial glass of water, it doesn't change the concentration of the water that was already there. It's a pure substance. It was just water. It technically doesn't have a concentration because it's not really like a mixture, so to speak, or a solution. What can have concentrations, though, are your solutions and your gases, okay? So just understand that solids and liquids, they're not going to be included in the equilibrium constants. So in the next video, we're going to practice writing some equilibrium expressions for different reactions using our general knowledge of an equilibrium expression over here. To summarize, though, what we saw in this video was how to graphically analyze equilibria using either the concentration versus time graph over here or the rate versus time graph over here. We understand that even though concentrations stop changing, it doesn't mean that particles stop moving, so the equilibria are dynamic. Equilibria is plural for equilibrium, by the way. So on the outside, it does look like properties have stopped changing. So we say macroscopic properties have stopped changing, meaning that the bigger properties that we can see don't change, but the particles still go back and forth at the same rate in left to right versus right to left. We also saw there's a law of equilibrium, which basically means that if your system's at equilibrium and you take a ratio of the products to the reactants, you'll get a constant called the equilibrium constant. And you can use that to basically decide if your system's at equilibrium or not. And so you can write an expression to figure that out. And so your K, uppercase K, you can write EQ next to it. There's different types of equilibria we'll see later on. Is going to be your basically products multiplied by each other to the power of their coefficients, divided by the reactants multiplied by each other to the power of their respective coefficients, as you can see over here. And then you can plug those numbers in, if you have them, and figure out what the K value is. Now, we also mentioned that the K is not reported with units because they're so different. K does change with temperature, so we have to specify what temperature it's recorded at. And solids and liquids, they're not included in your equilibrium expressions because they don't really have true concentration, so to speak. Their concentrations are constant because they're usually pure substances. So the only thing you will include are gases and aqueous. And so we'll see that in the next video.